affected, but immediately there is a decaying part here, so you can actually use that to study the properties of the top quark in a very direct way. Since it's so heavy, and since in fact the coupling to the Higgs is sort of order 1, people do believe that the top quark is probably something very special for us. It is a special part. We don't know why its mass is so high, but it's definitely very high, and we think it may well play a special role in electronegativity breaking, or in physics beyond the standard model. So often you will find in physics searches beyond the standard model the top quark as sort of a privileged type of quark to look for deviations or decays even of very heavy objects into perhaps top quark. Maybe that goes with a better coupling than to the other particles. Typically in extra dimensions in the model, for example, this can come back. The top production goes as follows. So top has been studied before and until now at the Tevatron in near Chicago, but the production mechanism they had there was quite different. They were actually dominated by quark-quark or quark-anti-quark type of production of top-anti-top pairs, while at the LHC it's basically gluon driven. This has consequences also, for example, for effects which have been seen at the Tevatron and how well one could possibly test these at the LHC. Now, top is of big interest also to the theory community, and for example, one has predictions for the production cross-section of top up to not quite next to leading order, but at least the dominating parts of next to leading order. So it's an approximation which tells us that probably we're very close to the next to leading order type of calculation, although it's not quite that hit. And these are the numbers what we expect for 7 TeV and for the Tevatron as before. And you see this enormous rise of cross-section which we have from going from the collider where it was studied so far until it was studied at the LHC. And that's one of the reasons why, for example, top physics as a physics field has ramped up very fast at the LHC. Also because the detectors are probably somewhat more extended and were quite tuned before we actually got the data. But since we got it, we got quite hang of the top quark. We became very rapidly a precision field in the LHC. After all, we're only taking data since 2 years. Even a channel like single top, which took like 14 years between the discovery at the Tevatron and of the top pairs, and then the single top, which was being isolated, was already done within a year at the LHC, as I will show. So these are top decays. We believe that the top is, or we measured that the top is decaying essentially always, maybe up to some small corrections, into W and a B quark. And the B quark decays, of course, fragments as a B jet, so it is recognizable as a jet with some B tagging. The W can either decay hadronically or leptonically, and depending on that, and since we have 2 tops produced in what I will discuss first, so the top and the top production, we will have 3 different classes of events which are typically used for analyzing. So one is where the W's, both W's decay leptonically, so we see 2 leptons, 2 B jets, and a lot of missing ET coming from the neutrinos, which go into the W decay as well. This is the mixed type of modes, and in fact it turns out to be, this is probably the most crucial one, which allows for the most precise studies at the top. Namely, 1 W goes hadronically and 1 W goes leptonically. The reason is that the branching ratio to go into the W's going hadronically is quite high compared to the leptonic ones. And it allows at least for 1 top to be reconstructed fully, while here you always have some missing ET coming around. Even more branching ratio and more events you get in this channel where both go to in a hadronic decay. However, while you get here a 6 jet event where 2 jets are B jets, here you have a lot of fights with the background, typically QCD, pure QCD events, which have no leptons essentially, and then it's more harder to tag this. So at the end, this one will be a very good one. This one is a very precise one, but you have these 2 neutrinos, so you miss more information. Now this is a real event actually. This is not a simulation. This is the beams coming in, the blue packages here, There's a collision coming out and particles being produced as they are tracked to our detector, of course, much faster in reality, but this is how it works. And what you see in this event is you have a couple of small jets and 2 muons you have in these events. In fact, if you analyze this event is completely compatible with, for example, such a structure. We see these 2 muons coming out. We have 2 jets which were coming out with some particles. In fact, if you look in detail, we can see that these 2 jets are jets coming from a B quark, because there is some signature in there which tells us it's not light quarks which produces, but it's a B quark. And the whole thing is imbalanced. If you look at that here, you see something is missing on that side. And effectively, if you add up all the vectors here, you find a missing ET like that. So this is what this event could be. You never can say, of course, for each event what it is exactly. But this is a good candidate for a decay where the tops decay into WB. These are the 2 B jets which you see here, and the Ws themselves decay into the lepton plus neutrino. These are the 2 leptons coming out. This is the neutrino sum of the neutrinos, which takes away the missing ET here. So that was actually one of the first events which we saw in the early summer of 2010. And that told us that really the top is knocking at the door and coming in to be studied. And the thing which we want to study, which is the first thing to know, which is very important, for example, for searches, which we want to do later, because the top signature, missing ET from neutrinos, B quarks possibly, leptons, is very similar to what you could get as signatures for SUSY and SUSY production of particles. And therefore it's very important to understand top production as well as you can before you go actually out and search for SUSY and maybe find something and say, oh, I have more events in my Monte Carlo than in my data than in Monte Carlo, so maybe I have a signature there. So better check your Monte Carlo, or better check with the data what the top looks like and how it behaves. And here we see these are the measurements before at the square root of S of 2G, 2TV at the Fermilab collider, 7 TV where we are now from 2 experiments. These are still early measurements which are plotted here, but it already shows that, you know, again, one would hope perhaps the top would be higher than what we would predict from the theory, but in fact it's quite compatible with what we would expect from standard model. Now this doesn't mean there is no new physics in the top sector, because this is the bulk, this is all the top events. These are now hundreds of thousands of top events which you put there, at least at present, maybe not yet for this analysis. And maybe there is a tail somewhere where indeed new physics sets on with 10, 20, 30 events or so. You wouldn't see that in this cross-section here. But the bulk measurement says you that we're in the right ballpark, and this is somewhat in detail. In fact, right now there are many measurements in all sorts of different channels, like the channels which I showed before, the different decay patterns of the top pairs, and with different methodology, either tagging on Bs, not tagging on Bs, using different techniques, and you see this cross-section are all quite compatible with what is our best knowledge of the theory right now, which is given by this sort of dark shaded band here. Now, the game starts because we have lots of tops coming available to us thanks to the high cross-section of, for example, measuring top mass. Of course, the top mass should be the same as at the Tevatron. There's no reason why that should be different. Right now, the fact that there is already more than 10-year experience at the Tevatron in getting the errors squeezed out as small as possible makes that still the Tevatron measurements are the best one for the top quark. But we are starting to get there within a factor of 2 or so, and I would say by the end of the year we will probably also overtake the Tevatron in precision measurements for example, something like the top quark mass. And you can ask many questions on the topic. Does it have the right spin? Does it have the right charge? Does it have all sorts of things? And these things are starting. Indeed, this is a measurement from the Atlas collaboration, looking at events where you have the 2 leptons in it, so the fully leptonic W decays for the tops, and looking at angular correlations between these leptons, and then they can see if there are certain spin correlations between the tops as would be expected, and they start to see that indeed this is the case with some significance here, following again what the standard model is predicting. An interesting measurement is the following one. It's a bit of a tricky one, but it's interesting because it's sort of, in our community, generates quite a bit of discussion. And this is in the production. If you look at the production, where in space, in longitudinal space, these tops are ending up. And for example, at the Tevatron, which is a proton-antiproton collider, you could have an asymmetry of where the top or the antitop is going. And in fact, the top is likely to go more towards the direction of the proton, which brings in U-quark, or which brings in valence quarks, while the antitop is going to be more likely in the direction of the antiproton, which brings, if you want, antivalence quarks. That's not trivial, because in fact in leading order there is no such effect at all. It's completely symmetric, and you would see, if you would look at the top antitop one, they would fall on top of each other. But at next leading order there are several interference effects which actually make that the distribution in pseudo-rapidity is sort of asymmetric for a top and antitop one. And that's one thing. This is predicted again by the calculations, although at the moment we have only next to leading order calculations right now, which means this is the first level at which we see this effect when we measure these forward-backward asymmetries. That by itself is not special. That's something actually testing the theory. If it were not that the effect that the data at the Tevatron shows there's a larger effect than what is perhaps expected. And in fact, you see here, this would be a symmetry of 0, the asymmetry measurement for different measurements which they have here. This is what the theory would tell us where it would be, which is at this next to leading order, which is the first order in which you see this effect. And this is where the data is lying. So it's somewhat on the high side. In fact, if you add everything up, it becomes like a close to 2 to 3 sigma effect. So we start taking this seriously. And new physics, again, for example, Z primes, which could have special couplings, could create this to be a higher asymmetry than what you would expect from a normal standard model calculation. So this is of interest. Now there is still a bit of data which has not been analyzed for the Tevatron, so we will see if this effect persists, gets amplified, or starts shrinking. That will be with the full analysis of all the data. And of course the LHC would be the next machine to look at that. If that's really a window to some kind of new physics, it would be interesting to explore that. Now the problem for the LHC is going to be that's a proton-proton collider. So you do not have this kind of effect. However, you can still have the correlation that the top is more related to a quark, while the antitop is more related to an antiquark which you produce. Antiquarks are now going to come from the C, not from the other proton, because it's only valence quarks we have. While the quark often will come from the valence quark, and as therefore the kinematic distribution nevertheless will be somewhat dissimilar because of this effect which I just talked about. And if you picture them more like this, that you don't see a shift of the two distributions, but a broadening of one with respect to the other. So you have to make a somewhat different measurement to actually see that effect, and it gets washed out for 2 reasons. First, because it's not as big if you see it in such kind of presentation than in this one. And also, as I said before, most of the tops or top pairs are produced by gluon-gluon interactions, which would not have this kind of asymmetry. So the asymmetries get small. Here, while they were here like 5% or more, and maybe like 10–15% seen, something like 1% or so is what we're talking about here, what we should be seeing. But the statistics does allow the fact that we're going to have 10 to 100 times more statistics from the LHC with the top quarks will allow to say something on that if the systematics can be kept under control. And this is the challenge of this measurement, keeping a very low systematics for making a kind of asymmetry in absolute values instead of in the direct values, and getting that out. And also there was some mass dependency, which apparently, if we look at that, we do find we are close to the theory, and we are not seeing any real big effect sitting out here, and we also don't see particular mass dependency. But this is a space to watch, and it's a very interesting topic, I think, for people who like this kind of standard model physics and look beyond standard model in this way. So it's a bit like if you want the Hera B type of measurement of an indirect search for new physics. Just for the record, so this is single top production. This is not top pair production, but single top production, which you get out here, which is an electroweak process. And as I said, it took 14 years at the Tevatron after they discovered the top quark, before they could actually isolate this process. In fact, there were, yes, there were more these two processes to isolate. And thanks again to the large cross-section and also to you know, the swift top analysis we had, first results already came out, in fact, exactly a year ago from the LHC, signaling that they observed this process with about 3 sigma significance effects. And I can tell you from more, you know, for the winter conferences which are coming up, there are now real interesting data with more than, I think, 100 times statistics, which is going to come, and you will see precision measurements already on the single top appearing there. This is, in all, the summary of electroweak processes as we get with W's and Z's. These are the cross-sections as measured with their arrows on it. The dye bosons, I didn't insist much on that. I showed one event just yesterday, which were next in cross-sections. Then this was the TT bar cross-section, which started to be probed, the single top cross-section, WWWZ and the ZZ bar and the ZZ cross-sections, which are of the order of a femtobarn. And for all of these, there are now measurements, and you see they're all sort of within the arrows of the theory, if you look at it in a very inclusive way. So for the standard models in measurements, I think, well, you know, we have, of course, for the Atlas and CMS experiments, their primary goal is to go out and search for new physics, but on the way they have to make this stop because you have to test the standard model at 70 eV. Surprises could show up. Our calculations could be incomplete, for example, and then we would need to adapt them. So far, no big surprises showed up. The biggest one I showed sort of yesterday, which is the W in association with D quark production, which is a bit off, and we'll see if that stays. But all the rest looks fine within sort of a 10 to 20% area for the jet production, where it's pretty the error on the data, on the systematics, which is driving that, as well as still large uncertainties also on the theory corrections of that order. And the electroweak measurements like WZ production, as I said before, they are on the order of a few percent. The top core cross sections actually we measure now up to 7% precision, which is of a similar precision as the theoretical calculations. And then one difference which I pointed out, but in all, we are in a good position to start to look for new physics. If we sort of have this in the pocket, at least we know generically how we can normalize the searches or the backgrounds for searches for new physics. So the rest of this lecture I will spend on searches for the standard model, for the standard model Higgs. And bon, to introduce the subject again, John Ellis will come here, I think, as of day after tomorrow, and he will give you the theory behind that. So I'm not going to go into the equations for all this because I leave that to him. But generically, what we are looking for is some messenger of a field which is postulated to give the possibility of particles to acquire mass, the elementary particles, that is. And that has this shape postulated of what we call a Mexican hat. So you see, this is the hat. This is the center of it, and at the center, this doesn't appear to be the position of lowest energy. In fact, the positions of lowest energy are somewhere around here. And that, in a nutshell, is what drives the mechanism, or what gives the mechanism for masses to particles. So you'll see it in more detail, as said, in a couple of days. But this is a scalar field, and with that scalar field, we believe there is at least one particle associated. If it's a standard model, it should be probably one. If it's some kind of an extended theory, which is appeared, it could be more, and it's likely to be more particles involved, and that is what we are looking for. So this question, this principle was already, as I mentioned yesterday, introduced in the middle of the 60s. So it's quite a while since that idea is around. Maybe it called up for people to say, well, a way of actually testing this thing is looking for this boson which is associated with that. which, by the way, will be a very new type of particle. It will be a scalar boson. We don't have an elementary scalar boson so far anywhere in this table which I showed before. These were spin and half and spin 1 particles, and maybe the graviton will be spin 2, but this would be a spin 0 type of particle, so it would be, as an elementary particle, a real new thing to see. So it should not be underestimated how important it is to actually establish if such an animal exists really or not. But so in the middle of the 70s, and I know John will give some historical introduction to that because he was involved in this promoting, I would say, Higgs searches into particle physics. And so searches, the question is, where is the Higgs? And this is CMS plus the Higgs, and this is Atlas plus the Higgs. But so it's maybe our first Higgs sighting, which we got a few years ago, but it's not enough evidence, I think, for this mechanism here. So we have to do a bit better. And what we do is the following. In fact, a Higgs particle, when produced in the standard model, and most extensions of the standard model, is a particle which is going to decay immediately. It's an unstable particle. There are exceptions in some theories, like hidden valleys and others, where this actually can be something that runs in the detector, but I will discard this for now. We look here for a standard model type of Higgs, first of all, which is also a good search in many cases for beyond the standard model Higgses, but there are more coming to that. And these are sort of a number of typical studies. This is simulation, by the way. Don't think we see a real Higgs signal here. This is simulation done years before we actually had any data, because a lot of these detectors, Atlas and CMS, were actually optimized to try to get as good as possible significance or sensitivity to this kind of channels. And the Higgs, in fact, we know, if it's a standard model Higgs, we know everything about the Higgs, except its mass. And if we would know its mass, we could also tell how particularly it would behave. For example, a very low mass Higgs, we know, for example, with what probability it would actually decay to 2 photons. And 2 photons happens to be not the best branching ratio, but it happens to be a very easy branching ratio for detecting the signal over background. Because this is one of the nasty things with the Higgs. Supersymmetry typically looks different from what you get from standard model events, except for tails, where you could have some contribution. Higgses look, in fact, like many of these standard model events you could have. For example, this is a Higgs of 140 GeV decaying in 2 photons. We have a lot of 2-photon production, normal QCD 2-photon production in the data. And on top of that, we even have fake 2-photon production, where this is actually a jet, but it's interpreted as a photon. That's the blue stuff you see here. And mind you, there is a zero suppression here. We start at 4,000 going up, so this histogram goes down here. This is simulation. And the Higgs would, the benefit of a Higgs, the characteristic of a Higgs is in this particular channel that these 2 photons would reconstruct to a peak, because it comes from a given mass here. The Higgs is produced with a fixed mass, with some width, but it's very narrow when it's at that low mass. So you would actually see it sticking up here with some width which is given by the detector resolution. Now nature isn't so kind to us that it colors things, the Higgs is red and the background blue, so we will have some kind of a mixed plot, as I will show you later for the data, of which we have to find back a peak. And of course, we will start with less data than what you see in this plot here, so at the beginning this peak will be barely visible, and then it should grow with time. Another golden channel, as we call it, is Higgses which decay not in photons but in Z's. Now Z bosons are unstable by themselves, they decay, and for example in 2 leptons, say 2 muons, 2 electrons, in this case it's both are going into 2 muons. So you can see a 4-lepton event in the detector like that, and that is again something easily recognizable because the background here will be very low. There are not so many processes that do that. In fact, pure ZZ production would do that, and some fake background, but not much otherwise. And so even with a few events, you could start seeing peaks here. Here you need very many events for statistical analysis. Here you don't need so many. And as you go up at higher energies, you can use other channels to deal with that. These are just a few channels. The Higgs, in fact, I will show decays in many more options. And in fact, we, in both experiments, look at all these possibilities but they all have a quite different sensitivity, and these are sort of like the main channels which are also going to come back for Roeck. Now, doing a Higgs analysis, as you can imagine, you start to see something growing on a background. You start with a few events which are coming in. So we have incredible analysis statistic tools which are actually attacking this. And I will give one word on it. In fact, you can give easily, I could give 3 lectures on statistics there, trying to convince you how you can dig out a signal with some confidence out of such a, such a thing. But you have to remember these wise words of Twain saying that there are 3 kinds of lies: normal lies, damned lies, and statistics. So be critical each time such an analysis comes with statistics, and I will try to weigh the words in the proper way. These are a number of plots which you will be seeing, so I thought I'd give you up front what you can learn from these plots, what is actually the message in these plots, so you can sort of appreciate more throughout what the experiments are now producing, and what they will be showing at the conferences, and what you will be reading in the papers, for example, is the one very recently produced. This is somehow the key plot. This plot, for the analysis of the standard model Higgs, which is what we are concentrating on most right now, which does not mean that we have our eyes closed for anything else, far from that. But what we see most is such a kind of plot, such a kind of, sometimes called a Brazilian flag type of plot. What you see here is, for a given analysis, for a given channel, or for a combination of everything, you have a certain sensitivity to actually be able to see a standard model Higgs. And the standard model Higgs, this is like a signal hypothesis test, what you're doing. You compare what you see with respect to the sensitivity you have for the standard model Higgs. That would be at 1. 1 is you're exactly sort of at that sensitivity. If you're above 1, you actually do not quite yet expect to discover the Higgs, although you can see an excess of events there, which would make your real limit work. So the red one is the calculated, if you want, theoretical, but it's not theoretical, it's the experimentally determined sensitivity, what we should be expecting. And that's of course smooth, because that's done with Monte Carlo, and this is as much data as you want. Wherever this, this is what you expect. And then the bands are, because there are uncertainties on that, the bands is 1 sigma or 2 sigma uncertainty away from this red line. So you can see, if you see something, how significant it is with respect to this band, with respect to this red thing. Interesting it becomes if you want to exclude, for example, a Higgs. That would happen if the observed one, the one which is actually using the data and analyzes that in the same statistical way, where that curve would go below the line of 1. And that we will see. This is where we see no Higgs signals coming up with the expected strength as predicted by the standard model, but of course always mind is 2 sigma uncertainties. Now here and there you may see in this graph, like for example this one, which is a real experimental result from Atlas, that there is a peak here, and you have clearly, if you have such a peak, it means you have more data in the analysis than what you would expect to have. So it means the exclusion of trying to exclude that Higgs gets, that mass region gets more and more difficult, so that moves away from that. So now you can say, how likely is this that this is pure background? And this you do when looking at what we call in statistics in the p-values, the probability values, that this indeed corresponds with the background. And that is, it does not correspond with the background with almost 3 sigma here. It's 2.6 sigma away from the background. So it means if you do a lot of experiments, it should be very rarely that you find this, 1 in a few thousand or so. So either you're just unlucky that you have a very big fluctuation in the data, or really there is something there which tells you there is more in your data than there is background. That's what that's saying. Then as a third thing, you can actually say, now I want really to see what is the hypothesis test for a given signal strength for example, a Higgs. And the signal strength is, if it would standard model Higgs, would be equal to 1. Again, you can put that in the statistics model, and you see, for example, for this fluctuation here, which says you can't possibly exclude that Higgs. In fact, you see an excess. The excess is somewhat large because it is away from the background, so it's unlikely to be background. Now, how likely is it to be a Higgs? So the standard model, well, it would have been around 1. Here it's actually above, so you produce even a few more events than what you would expect just to come from a pure background plus standard model Higgs included in there. Again, this blue thing is the error band here. So, well, this to give the idea, most of the plots we will discuss in this one, and some plots we will discuss that, and maybe at the end I'll show something on the signal strength for a real one. So, these are possible channels, in fact, which are being looked at. These are production mechanisms for the Higgs. So, gluon is the big line here. This is the dominating one. There are less sub-dominating ones, like this one, where you have actually a vector boson fusion of Higgses, and you have associated jets with that here. This is this one. And there are a few other ones where the Higgs is produced in association with a gauge boson. All are important, although these are 1 or 2 orders of magnitude less in cross-section. The fact that they look more special, because this is very inclusive, just this Higgs, so like just these 2 photons produced. Here you have additional tools to tackle the background. And so the signal to background typically for these looks much better than for that one, but of course you have a penalty of the cross-section. On the other hand, the Higgs decay, so not only the production mechanism is some characteristic which you can use, but obviously the decays are what you have to use. And if the Higgs is light, we have already seen the 2 photons, which is a very good channel for there. In some region also this 4 lepton channel from ZZs is important. And there are a few others which all have the characteristic that you actually are not able to reconstruct the Higgs mass very precisely. 2 photons, 4 leptons is very precise because we can measure photons and leptons very precisely. We cannot measure 2 BB jets very precisely. They have a resolution which will go up to 15 GeV or so. And in the taus there will be neutrinos as well. In most of the W channels we look at here, there will be neutrinos escaping, so that the information we have is incomplete. But all of that adds to finding evidence for Higgses. In the higher mass regions, it's basically going to the gauge bosons and the different channels which we look at here for finding Higgses. This was the situation last summer at the Lepton Photon Conference in August. And this is the plot, as I said before. This is the expected value, and this is the actual data which we see here. So each time it goes below 1, we have excluded a standard model Higgs with exact standard model couplings. It does not mean some type of Higgs of that sort could be here with a coupling which is maybe 5 times or 10 times smaller than that. So we will dig in and see if at the end we see some excess here, but it doesn't look like it. We even see less events than what we would expect from the background estimations here, which could be, of course, a fluctuation. Where it comes above 1, there is where a Higgs could start, but still we expect here not to be able to exclude much because our expectation is close to 1 here. Here we expect to exclude a lot, and we do, but we see also something, pushing up here, which doesn't really want to be excluded. This is in the Atlas case. In the CMS case, there were some ranges excluded, but the more interesting part was, I think, when we combined the data, which we did in November, and then we got this kind of whole range excluded here, and so only the Higgs could exist. The standard model Higgs could exist with its couplings, as standard model, in the high mass region, which is somewhat disfavored by, well, it's heavily disfavored by electroweak measurements and somewhat disfavored in most of theory's minds as well, I would say. While on this side, we could not exclude, in fact, we could not exclude as much as we thought we would be able to exclude if it would really not exist, because then we would exclude up to this point, but here we cross over, and in fact here something may be building up. Now this was with 1 to 2 inverse femtobonds, and then of course the accelerator went down and produced of the order of 4.5 inverse femtobonds, which is what we are looking at next. Now in principle, well, these are, for example, the updates which came at the end of the year, in December 13th, which was already mentioned yesterday, for these several channels, as done in this case by CMS. They update like 8 channels, which have their range where they can give information, the luminosity used, the mass resolutions, and you see indeed the ZZ to 4 lepton is 1 to 2% mass resolution on the Higgs, 1 to 3% for the gamma-gamma, but all the others have a much larger one. Maybe this one is still fine, but that's only the high mass. Well, yeah, there's also low mass part now. And so here you can see what channels we actually all have available as sub-channels even in here. So in principle I could go through all these channels, but I believe there is a contributing talk in the Young Scientist Forum where these channels will be reported, so I will not go to each channel individually. For the sake of interest, they are in the talk, so you can look at them for different channels, what they contribute, how they work, how the events look like, what the exact diagrams are which we are studying, also some standard model Higgs exclusions which we are having, BB channel, very difficult, however we're getting, and the WW channel, as I said before, tricks we are using with angles to increase the sensitivity, but I leave it to the speaker in the session. I will say just something about the 2 main channels, and one is, for example, a 4 lepton channel. This is a 4 muon event, as you see here. So again, this diagram as we had before, and again, that's a very important one because it has such a good mass resolution, low background, but it suffers a bit from statistics. Again, for example, one of these events shown here with the muons nicely spread out, and some ways in which, I will not go in detail in that, some ways we have actually improved the analysis with respect to what we've shown in the summer conferences. And this is sort of the result. This is, if you look at how many events you had, maybe a bit few to see from the back, but typically we observe 72 events of 4 charged leptons, so it means electron pairs or muon pairs are all intermixed here, and we expect something like 67 plus minus 6%, so there's 6 events, so there's no real sticking out evidence that you would see here, but in some regions some events are grouping, and if you look in the small mass region, for example, you see 3 events here aligned at 119 and a few events aligned at 126, and it's that, with this kind of statistics, what we expect to grow up if somewhere there would be a signal sitting around here. This year we're going to have 4 times that statistics, so it will be interesting to see how that evolves. And we find limits, and this is the whole mass part for the ZZs, but this is the interesting one, this is the low mass part, and you see again we are excluding this part here, but here somehow we see more events than what we would expect in this small mass region here. The second one I will mention is the photon-photon. So this is a nice event where you see 2 electromagnetic clusters measured in our crystal calorimeter, and that's typically how such an event could look, but as I said, there are also QCD processes which do that, so it's always a matter of a signal over background here, and this is at the moment what our spectrum looks like, and now the whole discussion is on this point here. Do we actually see something stepping up here, or is there something that falls too low? Is there a compensation? But the statistic analysis does give you that here. So small down here and then some undershoot over there. Okay, these are all the channels, it's not so important. This is then the sum of everything from the CMS experiment alone. You see everything now falls up to 600 GeV below the red line, so that's where we exclude at 95% confidence level the standard model Higgs to live. But on this side, you have some channels which are starting to get in resonance, to get in accordance with each other, and you see something sticking out here. So not only we cannot exclude this region, on the contrary, we find an excess of events in there. It's not a very big excess at this point, and if you analyze it, and you do this kind of local p-values, in fact we see 2 values in this plot here because of the accumulation around 120 of these ZZ events, and this is for the diphoton event. So the maximum we have is actually like 2.6 sigma. Normally we talk about observation if it's more than 3 sigma, and about the discovery when it's more than 5 sigma. So we're quite a bit away from that. Moreover, if you don't know exactly where to look in your histogram, where you would like to see an excess. In some analysis, when you look for a particular particle, you know the mass exactly, you can exactly say, here, this mass, this is what I test, and that's exactly where I should see an excess or not. We don't know that, we look over the whole range. And then there's a statistical issue which is called the look elsewhere effect. So how often could you create randomly, statistically, somewhere an excess of that sort by this so-called look elsewhere effect? Take them out of the battery here. Okay, so if we correct for that, what you do is you can calculate a statistical penalty for this number because you didn't look at the specific range but at the whole range. And then if you take the whole range, which is probably too pessimistic because we knew already the Higgs doesn't exist in quite some big range for that, you get a very low probability. If you look only in the region which you couldn't exclude before yet, you get something like 2 sigma. In any case, it is a tantalizing effect, but it is not yet a proof for having discovered the Higgs at this point. And this is the signal strength, this mu, which I said before, and it gives you that indeed, yes, if you add in, you take background, you add in a standard model Higgs, you would find about the right strength here of the signal, about 1 here, which is actually amazing. That is independent of the statistics you're having. Of course, with the 50% uncertainty, because the statistics is still low, but it's actually tantalizing that you see that it is maybe. So then the question is, what do atlas see? Because this is one experiment. And typically one says once every 1,000 experiments you could see, or in this case every 100 experiments you could see this kind of excess. But if you have a second experiment, what does it see? So Atlas also made an update at that time, and they showed only a few channels, concentrating on the low mass range, particularly, because that is where we didn't exclude anything yet, so that may be the most interesting to look at. And they looked at W's, which I will skip, but they looked, for example, at the 2 photons, and they see this. They see this peak, if you want, here, above things.
Is it peak?
Yes, of course. Whether it is Higgs is a different story, but statistically speaking, this is kind of a peak. And you see that being translated into this, this statistical analysis as this one here. Now the interesting point is, well, and this is again the p-value, which is actually also 2.8 sigma, so when we look elsewhere effect it becomes 1.5 sigma. But it's 2 experiments now which are seeing something happening in the same region. Could still be statistics, could still be chance. So what you need definitely is more data. You cannot conclude from these 2 measurements that you actually have observed the Higgs. What you can conclude is that if a Higgs were to exist here, this is exactly the way it would start now. Because we don't have the statistical significance yet in this region to actually discover a Higgs. But we can't exclude it, and it is growing in a way which you would expect, because you see the signal growth which I saw on the previous slide to be of order 1. Could be chance, could be fluctuation, could be anything, but it's not all. Also, you have these 3 events which are accumulating here, which in the ZZ channel, which again maybe by chance, but it's another channel you look at, it's completely independent of what you looked at before. You could see these events here. Now you say maybe there are missing events there, they're all sitting here. Quite possible. You expect something like 1.5 events from background, you see 3 events. Again, not to write home about, but with 4 times the statistics, I think you should really clarify. So that's one of the events. This is also their plot, which I will not go in. And this is their combination, which I think, and this is the full mass range, which is maybe less interesting. This is the low mass range. Similar type of behavior here. I will show how similar it is in fact in the next slide. But this, the channels sort of add up even better in the Atlas case, where the 2 photon and the 4 lepton events are falling in the same region. So around 125, something may be happening there. And this is the exclusion which we have now from Atlas to this. So this is where the Higgs, the standard model Higgs, could live. In this region here, between 115 and 130. In fact, in CMS it's even 127, so it's only a small region yet to go. It's the most difficult region for us because it needs the largest statistics to be able to probe it fully. But the interesting part is you see something like an excess in both cases. These are the things for simulation. Okay, somehow plot disappeared. Where this is the Atlas. This is the Atlas and the CMS observation which we have here. Okay, I actually had another plot which I overlaid in some way. So there is, if you want, a few GeV shift difference. This is more like 123 GeV, where you see the sum of everything sticking above. This is more like 125 GeV. Does that mean the experiments are not calibrated? Well, no. This can mean, well, it could mean that, but we believe that's not the case. What could be the case here is, again, statistics. If you have a very small effect on a background which is fluctuating, the fluctuations in that background actually will shift your peak, or not peak, or whatever, your axis, if you wish, from one side to the other. Within a few GeV, this can happen. This we have seen with toy models, so this is not incompatible, what you see here, even without having to deal anything on more statistics. Here it is. So here you see how it's actually compared. It's a bit difficult to see because the sensitivity bands are different. There's more sensitivity in CMS because they've included more channels than in Atlas, so that this thing gets a bit ducked in here in the Atlas band, but this is somehow how the two things compare. This is an unofficial plot, by the way, which I picked up from a workshop. This is not even a combination, it's just a comparison. All right.
So
now,
they overlap better on higher statistics?
So, let me tell you what's going on now. So with more statistics we have to wait for more collisions, and this starts only in April. And we'll see. If it is caused by the background fluctuations, then that should smoothen out, and yes, then they should overlap better in future. If it is another kind of issue, then of course not. And if it's just random fluctuations which we are comparing here, anything can happen. But what did happen is that there was an update recently, and in fact some papers were put on the web last week, in fact. In the case of CMS, there was an update in the fact that they also included a new channel, the so-called vector boson fusion channel for the two photon events, which is that where you have two jets being produced and a Higgs in the middle. And as I said, the cross-section is lower, but the signal to background is better. And this is the sum of the thing. So, in fact, our peak here, without wanting that, or without particularly targeting for that, somewhat increased from a 2.6 to a 3.1 type of significance. Now, it's still, with the look elsewhere effect, 1.8 only, but what it does tell is that two channels, a new channel added to that, which wasn't there before, adds to the significance of this thing here. And if you look at that channel separately, it has a similar peak as what you see here. Now that all becomes a lot of coincidence you are having here. Yet we can't, because this is the channels, I think, this is the ones we had before, and this is how this new channel adds in here. So you see, it shifts the peak from 125 to 124, what we are having, but it gives this kind of thing. Anyway, it is just to give you the appetite for what is going to happen next year. Nobody's going to claim anything on these kind of plots here, but there's a lot of things seem to go on. You see now also the total exclusion plot going to this kind of excess here. And these are the p-values. This point is receding here, but this one is sort of getting stronger in this new analysis which we gave. This is again the strength plot which I showed before, so you're still sort of compatible with one for the Higgs mass hypothesis. So, wrapping up, what will the data tell us this year? And we expect something like 20 inverse femtobarn in total, which means like 4 times the statistics we have this year. And that should actually be enough on statistical basis, given of what we see now, to see if that axis, what is there, is for real, or it is, a statistical problem in the background, problem or a fluctuation in the background. And there are some curves here which show even with 10 inverse femtobarn and 7 TeV, in fact we're going to run at 8 TeV, so it will even be better than that. what we could do for an observation. And here's the 5 sigma line, and here is sort of where we're sitting with the mass of 125 GeV or so. So we're sitting close to the 5 sigma line, but we will have twice that data, and we'll have higher energy. We should be sitting above 5 sigma for each experiment to actually say independently whether that is indeed a new particle there or not. So the experiments analyze this new data. They can exclude a very large range, like, and then what is left for the Higgs, the standard model Higgs to live is something between 150 and 130 GeV. And you should behold the progress made in 1 year's time on our understanding of the Higgs. I mean, there were papers scattered around having Higgses all over the place for you know, like a year or 2 years back or something like that. At least with these couplings, we have narrowed that down. We know now there is no standard Higgs, as we would imagine it, living outside this area. Whether it's living inside this area, you know, this is, the jury is still out, and then we will see with the data if this excess indeed remains. But it is exciting. We could have seen no excess whatsoever. We could have seen probably even a better exclusion range like that. And then, you know, people would start thinking very, very seriously that certainly a standard model Higgs would not exist. That hope or wish is put on hold because it looks like something may be building up there. But we'll see. And the data 2012 will be the referee. And I told you the warning on statistics as we are having. So we will be still caught by a bad surprise in that if it was indeed some kind of fluctuation. But if there would be indeed a Higgs living on that, that would be actually the signs of life that would be starting to show right now. These are some plots, and this is what is left on, for people who know these electroweak fitting plots. This is what is left for the Higgs to exist in that standard model picture. A very other interesting thing, I think, which John will point out, is that if the Higgs mass, here is the Higgs mass, here is the high scale, and here is where the standard model gets unstable. And so it gets unstable when you cross any of these colors here, so the yellow one to start with, and it gets unstable when you get out there. This is to potential blow-ups, this is for electroweak vacuum stability. There is a corridor which a Higgs mass could have to live with the standard model all the way up to the Planck scale, which would be boring, needs enormous fine-tuning, blah, blah, blah. But it could happen. However, since we have excluded this part now, this corridor is closed for a standard model Higgs. We will hit new physics somewhere, but it could be very high. It could be a 10 to the 10 GeV. It doesn't say. It doesn't guarantee the LHC would actually see it. But as if this stays and these theory calculations don't change too much in future, they depend, for example, on the top quark mass, then we can say soon that there will be new physics around somewhere at the scale up to maximum 10 to the 10. And also note that the Higgs is often called, you know, we say, yeah, it's just a Higgs particle and that's it. But it could be really a portal to a hidden sector here. It could really look like standard model-like, but maybe it isn't. And so we will have to study that in very much detail, because this could be our gateway to find out what is on beyond the standard model as well. Personally, I like this comparison a lot. For the more senior people in the room, they may remember, well, I was still very young at the time, but I do remember the Apollo 10 moment. Now, the Apollo program of NASA, they went to the moon, and of course Apollo 11 is very well known because that's the one who actually set foot on the moon. And then, but people forget sometimes Apollo 10. Apollo 10 was the dry rehearsal of the whole project. So they went all the way, they went around the moon even, they looked at the back of the moon, they just didn't land on the moon. And somehow we're in a similar situation right now. So we did everything, we did the dry run, everything is set up. We see something of interest, we know it's possible to discover the Higgs in the coming year, but we haven't done it yet. At this point they wouldn't know if Apollo 11 would actually work really or not, they would actually be able to land. So we don't know that either, but I think we are in that type of excitement right now as NASA must have been when the Apollo 10 mission worked, and we are really eager now to get this new data sooner rather than later. And that will...
Yeah, we knew that moon exists, right?
What?
We knew that moon exists.
Yeah, I'm not talking about the existence of the moon, but I'm talking about the project being successful. There's always somebody who said, let me just summarize. The only thing I added to the previous slide on the standard model is that we see some axes here. Do we start to see the bird of Higgs around 125? Let's see during the year. I would say already this summer we will know more, because we will probably have double the statistics by then, and by the end of the year, quadrupled it. Okay, I'll stay here. Thank you.